First speaker of today is Michele Arzano, who will tell us about getting hot without accelerating vacuum thermal effects from conformal quantum mechanics. Thank you.
All right. Put it here. Let me see the pointer. All right. Very good. Okay, thank you. Thanks to the organizers for the invitation to give this talk. And well, let me start from a very basic and profound fact, which, however, has far-reaching consequences in quantum and semi-classical gravity. And this fact is that in quantum field theory, the notion of vacuum state has no universal meaning. To put it in the words of Paul Davies, before the 70s of last century, nobody really thought much about for whom the vacuum state of a quantum field appears devoid of stuff. Okay, so one very well-known consequence of this fact is that, for example, in Minkowski spacetime, the vacuum state for a quantum field associated to inertial observers, so what is the vacuum state for inertial observers, is perceived as a thermal state to uniformly accelerated observers. And this is the well-known Unruh effect. Okay, this is one of the consequences of this non-universal character of vacuum state in quantum field theory, but we know that in curved spacetimes, there are even more examples. For example, this fact is also responsible for the thermodynamic behavior of black holes, and that one of its consequences is ultimately the information paradox, and also the fact that, for example, black holes carry an entropy which is proportional to their area, and we really do not know what are the underlying degrees of freedom which make up this entropy. So let me go a little deeper and explain a little bit why is really that the notion of vacuum is not universal in quantum field theory. Well, let me restrict to free quantum fields. So this ambiguity essentially traces back to the possibility of having different choices of time-like killing vectors, which you can use to describe the time evolution in your system. And this time-like killing vector defines your notion of time, and basically you use it in the quantization of the field. It is used in the quantization of the field to decompose the space of solution of the equations of motions, for example, for the scalar field of the Klein-Gordon equation, into positive and negative energy subspaces. Okay, and these subspaces, the positive energy subspace is used to construct one particle Hilbert space, and then from this you introduce your Fock space, so the notion of particles, of many particles, and your notion of vacuum. Okay, so the main reason I'm here today is that if you focus on conformal invariant fields, the possibility of choices for time evolution extend to conformal killing vectors. Okay, and there have been some examples of this in the literature, and here I'm again restricting to Minkowski spacetime. For example, one could use dilations as generators of time evolution in two-dimensional Minkowski spacetime, and you quantize the field in a future cone to obtain. This was done by Wald recently, but it's appeared also in the literature in the past, as I will review, and obtain a Milne quantization of a massless field, for example. Milne quantization because essentially to use dilations as time evolution corresponds essentially to consider conformal time evolution in a Milne universe. I don't know if you know it, I will review it later, but the Milne universe is simply the future cone parameterized in hyperbolic coordinates. And of course, this Milne quantization, of course, same way as Rindler quantization in the Rindler wedge, should lead in some way to a notion of Milne temperature, in the sense that the observers evolving according to dilations should observe the inertial vacuum as having an unvanishing temperature, and I call this the Milne temperature. There are other types of conformal Killing vectors that you can consider in Minkowski spacetimes, and these are the ones that describe world lines of accelerating observers whose lifetime is restricted within causal diamonds. I will see this more in detail. And also in this case, Pierre and Rovelli, quite a while ago, proposed that in analogy with the Unruh effect, also these observers should perceive a non-vanishing temperature in the inertial vacuum if their accelerated trajectories are restricted to the causal diamond. So in this talk today, what I will do is to actually try to give a new unified group theoretic description of both Milne and diamond temperatures using a correspondence between radial conformal symmetries in Minkowski space-time and time evolution in conformal quantum mechanics, the one-dimensional conformal field theory. So let me start with the real stuff. Let us consider Minkowski space-time in spherical coordinates, and let me consider this generic radial vector field. Okay, now I impose the conformal Killing equation, and this can be solved, this equation, and you obtain that the most general radial conformal Killing vector as this form. This was done by Herrero and Morales in this paper. And here you have a time derivative with respect to radial coordinates, and A, B, and C are real constants. First key observation. So this most general radial conformal Killing vector can be written in terms of three generators, K0, D0, and P0, which generate respectively special conformal transformations, dilations, and ordinary time translations. Okay? These three generators close the SL2R Lie algebra. Okay, these are written explicitly here, these guys. And they can be classified according to the sign of this determinant here, delta. So for delta negative, you have so-called elliptic transformations. So a representative of this is the generator of rotations, which can be written in such a combination of P0 and K0. Notice here the appearance of a scale with the dimensions of length alpha, which is needed to obtain a dimensionless generator from dimension full generators P0 and K0. Okay, this alpha will be playing a key role throughout the talk. For delta equal to 0, you have so-called parabolic transformations, and these are generated by, for example, P0 and K0 themselves. And for delta positive, we have hyperbolic transformations, and these are generated by the generators of dilations, and this generator, which I call S0, okay? And the meaning of this generator will be clarified in the following section. Again, you see this is essentially the same combination of P0 with K0, but with a minus sign instead of a plus sign, as in the case of rotations. So, as I anticipated before, D0 generates conformal time evolution in a Milne universe. So you take the future cone of Minkowski spacetime, and you reparameterize. Well, you write this change of coordinates here. So you define new coordinate T bar and chi, and you see. So the metric becomes this one. This is a metric of Milne universe. The universe whose scale factor is T, essentially, T bar. And you see, this change of coordinate is very similar to the change of coordinates you do from Minkowski to Rindler, but the role of time and space are exchanged. Okay, so usually in Rindler spacetime, this T bar here corresponds to Rindler spatial coordinate, and chi to the Rindler time coordinate. As I said before, this S0, well, I didn't say, but I said that I would clarify the meaning of this of this generator. This generator S0 basically maps a causal diamond of radius alpha into itself. This was shown by Jacobson in this paper here. And essentially, it generates evolution in diamond, in what I call diamond time. So these are the orbits of the transformation generated by S0, and essentially it generates evolution in proper time of uniformly accelerated observers with a finite lifetime. Okay, so these are the trajectories of these guys. So let me observe now that if I restrict to word lines of moving along constant radius, okay, or on the light cones, the most general conformal killing vector, radial conformal killing vector, becomes of this form, okay, where I introduce the new time coordinate tau, okay. And the key observation is that this is formally the same, it's formally identical to the most general generator of, so this is the generator of conformal transformations on the real line. So you take a real line, and this is the generator of conformal transformations of the real line. Okay, and on the real line, this P0 generates translations in what I call the inertial time tau, which cover the entire real line. Then I can define a new time variable, which I call nu, such that d0 over alpha is equal to the derivative with respect to this nu. And why did I put the alpha here? Because d0 is dimensionless, so I do need to restore, the right dimensions. And you find the relationship, you can solve this equation, and the relationship between nu and tau is the following. And you see that evolution in time nu that goes from minus infinity to plus infinity only covers either half, the positive half real line, or the negative half real line, okay? So these observers that evolve according to this time as sort of a horizon at the origin. And the S0 here, you can consider another time coordinate, which I call sigma, which corresponds to evolution with respect to this S0 hyperbolic conformal transformation. And this sigma, this what I call the diamond time, you see that it covers only a segment of the real line, okay, of length 2 alpha. Okay, so now I come to the crucial point of the whole story today. This generator, which I saw before, this psi, corresponds to the most general generator of time evolution in conformal quantum mechanics. What is conformal quantum mechanics? It's essentially a 0 plus 1 dimensional quantum field theory invariant under the conformal group. This was studied in detail in this beautiful paper by Alfaro, Fubini, and Furlan back in the year I was born. So you essentially consider this is your field, Q of t, and this is the Lagrangian of your model, G is a coupling constant. The generators of SL2R, okay, in this case I take the quantum mechanical counterpart, so I multiply these guys by I, and these become H, D, and K, okay? Can be canonically realized in terms of Q and the canonically conjugate momentum P in this way, but this is not really relevant for us at the moment. What is relevant is that this model can be interpreted as a conformal field theory in one dimension, as was shown by Jakov, Chamon et al. In these papers. Essentially what you do, what they did, we consider some cats labeled by the time tau, on which the generator of inertial time evolution acts as a derivative. And in order to characterize these cats, you look at the reducible representations of SL2R algebra, and basically you define ladder operators considering this combination of K, H, and D, okay? And you introduce new cats, which are labeled by integers N, which are eigencats of the generator L0, essentially a rotation. And these eigenvalues Rn are related to essentially the eigenvalues of the Casimir, so which determines this R0, and N here are integers, okay? and different values of R0 label different irreducible representations. And L plus and L minus act as usual, raising and lowering the eigenvalue of these cats. So you can actually go ahead and solve this equation here. Okay, if you write down these guys in terms of derivative with respect to tau, and you obtain, as the Jativ et al. Did, that the tau states can be characterized by their overlap with n states as follows. So this is the actual function that you obtain by solving that equation, and you can actually take the product of two of these guys to obtain the inner product between tau 1 and tau 2. Okay, and what so this is considered in their work as the two-point function of the CFT1. Okay, and notice that, very importantly, for R0 equal to 1, this is basically the two-point function corresponds formally, it's formally identical to the two-point function of a master scalar field in Minkowski spacetime, evaluated along the word line of an inertial observer sitting at the origin. Okay, this is very similar to something that has been done for the sitter spacetime by these guys. Basically, they observed that essentially the two-point functions of static patch observers can be described by conformal quantum mechanics. Okay, something very similar to what we're doing here. So you can rewrite this CFT1 two-point function in this way, where this tau equals 0 state is obtained from the ground state of L0, okay, using this, acting on this with this operator, exponential to the minus L plus, okay? And from now on, I will restrict to the representation R0 equal 1. Crucial observation, very important, is that as it is well known from quantum optics, these ladder operators can be realized in terms of a pair of creation and annihilation operators, okay? So L plus given by A dagger L, A dagger right, I call them L right, I could have called them 1, 2, or whatever you want, it's just, you know, pairs. And thus, this equation discovered by Jativ P et al. Can be rewritten in this way, showing that the n equals 0 state has a bipartite structure, okay? It is naturally divided in two subsectors. Now, let me notice that you can realize this algebra here also in terms of another combination of the SL2R generators, namely this one, where L0 is identified with I times S, okay? And so we come to this picture that you sort of have two sort of vacuum-like states. I put quotations, which I didn't put on the slide, because you are really in quantum mechanics, so there's no Fock space. But let me call this vacuum-like states. So this n equals 0, the ground state of L0 of IS, it is sort of a Bulwer vacuum, okay? And is it basically the ground, with this identification, is the ground state of the generator of my diamond time evolution, the time evolution which restricts me to the segment. The tau equals 0 state, I call it Arthur-Hawking vacuum. It's the inertial vacuum from which we build the two-point function, okay? And as I will show in the next slide, as in the real world, the Arthur-Hawking vacuum is a thermofield double state built on the bipartite Bulwer vacuum. In order to do so, let me take the definition, this construction of the tau 0 vacuum state of the Arthur-Hawking vacuum, okay? And let me rewrite this equation as follows. Okay, I just write it in terms of the creation and annihilation operators. Okay, and what I obtain at the end of the day is that tau equals 0 is really this infinite combination of these n states, left and right. Now, so at the end of the day, I can write this tau equals 0, my Arthur-Hawking state, in this way. Let me take a little mini detour for those of you who are not familiar with the notion of thermofield double. Essentially, if you take a quantum system with Hamiltonian H and energies EI, you can build the thermofield double by doubling the degrees of freedom of the system. So you write this sort of combination, and you see that if you trace over one of the copies of the system, basically the density matrix of your thermofield double corresponds to a thermal density matrix at the temperature 1 over beta. Okay, so essentially this state here can be seen as a thermofield double state at temperature 1 over 2 pi alpha for the Hamiltonian S over alpha, which is the Hamiltonian which generates diamond time evolution. And this is exactly the diamond temperature derived for diamond observers moving along this trajectory here, the central one, by these guys, Sue and Ralph, in this paper, where they use a detector coupled to the field. Okay, it's exactly the same diamond temperature. Now, it turns out, as I showed before, that S and D belong to the same class of generators of hyperbolic time evolution. So there must exist an SL2R transformation which maps one into the other. This map is easily found if we introduce a new time variable tau prime, such that the generator of dilations written in terms of tau prime is equal to the generator of this diamond evolution written in time tau. Okay, and this is, you can solve this equation, and this is what you obtain. And well, note this is this corresponds to a map which was used in this paper, this very famous paper, to derive the diamond modular Hamiltonian from the Rindler one. So if you write the transformation in light cone coordinates, this is exactly this form, this coordinate transformation. You take this map, and it follows that this leads to this other identification of ladder operators with the D, H, and K. And you see now that L0 is identified with ID, but D, as you remember, is the generator of dilations. And so now n equals 0 can be seen as a CFT1 analog of the vacuum state associated to the generator of Milne time evolution D. So this time evolution determined by dilations. And thus, the inertial vacuum tau equals 0 now is the thermofield double for the Hamiltonian D over alpha at the Milne temperature. Td is equal to 1 over 2 pi alpha, as was shown again in this paper by Olson and Ralph, that observer restricted to the future cone evolving according to this Milne time observe the inertial vacuum as a thermal state at this temperature. So last slide. So, as shown by Herrero Morales, observers whose world lines are integral curves of a time-like radial conformal Killing vector are accelerated. So these are accelerated trajectories. And this is the modulus of the acceleration here. A is this coefficient here, it's not acceleration, okay? And delta here is the determinant, and omega is this combination of A, B, C, and T and R. So, for integral curves of the generator of dilations, the world lines of so-called Milne observers, A is equal to C is equal to 0. And this implies that these guys are not accelerating. Okay. For integral curves of the generator of diamond time evolution, so for diamond observers, we have this identification of the constants, and you can see that at r equals 0, so for the observer moving along the central world line, the world line passing through the origin, omega is infinity, and also these observers are not accelerating. So the bottom line that you can get hot without accelerating if you enjoy conformal symmetry. And there are some conclusions here, so if I have time, maybe I'll do, no. Yeah. So basically, what I showed is that conformal quantum mechanics, seen as a CFT1, is rich enough to reproduce vacuum thermal effect related to the freedom of choice of time evolution that you have in quantum field theory. And the evidence for the diamond and Milne temperatures has appeared in the literature in bits and pieces, scattered around, mostly only for the 1+1 dimensional Minkowski spacetime case. So what I did here, I used the correspondence between radial conformal flows in Minkowski spacetime and time evolutionary conformal quantum mechanics to gather group theoretic evidence for the existence of this Milne and diamond temperature. And basically, you see that the inertial vacuum appears as a thermal state to all observers whose time evolution is not eternal, according to what I showed. So, for a bit of an outlook, it turns out that the thermodynamic properties of this, so from what I showed, it is suggested that the thermodynamic properties of the Milne patch of Minkowski spacetime and of causal diamonds are deeply connected. So could this provide some new tools for studying entanglement phenomena and entanglementary Minkowski spacetime? I don't know. So I end up here. Thank you very much.
Thank you. Thank you very much. Questions?
Thanks for a nice talk. So it's not the first time that we see thermofield dynamics in this contest, but usually this happens when, first of all, you have a field theory, an infinite number of degrees of freedom in the game, and second, from the early days of Israel, but then later on Maldacena himself and other people, you sort of give meaning. In the language of thermofield dynamics, you usually talk about the degrees of freedom and the twig degrees of freedom. That's a typical. Then you say left and right, but you also said you can call it 1 and 2, whatever. So my first question is, you'd be talking about quantum mechanics all the time, and then at some point, some field theoretical structure popped up. And so it is a big jump.
Which field theoretic structure?
The thermofield dynamics. So you have an infinite number of degrees of freedom. Otherwise, it's just formal. It is only a formal analogy.
No, you can construct the thermofield double for a harmonic oscillator. That's essentially what you have there.
Yeah, but then if you want to give, meaning to the temperature, that's the only issue about what you have. If you want to call that thing a thermal state, then you better have a field, don't you?
Well, but the whole point here.
On top of that, the question is dark.
Yeah.
No, the question is, what is your interpretation, the physical interpretation of degrees of freedom and twilda degrees of freedom? In the Israel thing, for instance, it's inside, outside the horizon. Do you have such interpretation?
Okay, so what I didn't show explicitly is that you have two copies here of the thermofield double, and you could think of it as some degrees of freedom. For example, in the case of the diamond, some of these degrees of freedom of one copy is the ones that are inside the diamond, and the other the ones that are outside. Or in the case of the dilations, you have some degrees of freedom in the positive half line and some degrees of freedom in negative half line. Okay,
that's an horizon kind of thing.
And the origin it acts as an horizon. I didn't show it explicitly in the papers that this is the case, but in the first paper, I actually didn't use the thermofield double, but I used the 2-point function. So what I did, I said, okay, let's look at these observers, for example, diamond observers moving along the word line, central word line, going through the origin. Okay, and I consider the 2-point function written in diamond time, and it turns out that's periodic in imaginary time. So that's basically a thermal state. Yeah, so it's the other way of deriving the temperature. Okay, so this is like in the spirit of this word line quantum mechanics that these guys did also in the Sitter space. So you have you can derive these temperatures and do. No, the Anino, Sartnol, and Hoffman. It's called, yeah, I cited it somewhere. But basically, they do it for static patch observers in the Sitter space time. And they look at the particular word line of a static patch observer, and they observe that the 2-point function can be described in terms of conformal quantum mechanics. So the idea is that your field theory reduces to a conformal quantum mechanics on some specific word lines. Okay? So this is the picture. That's why you lose sort of the degrees of freedom of your field theory.
Is this because you wash away some degrees of freedom to the conformal? Some degrees of freedom just squash to one?
Yeah, because you consider just, you eliminate, by considering only word line, you just, yeah.
Okay, thanks.
Wonderful. I don't think there are any questions online. So if there's one short question here, we can have one more question.
Thank you. Just on the quantum mechanical side, is there any concrete system where you can realize this this CFT one dimension, where we can measure this temperature, maybe concretely?
It turns out that yes, there are the conformal quantum mechanics can be actually, there are systems for which you can realize this potential. I can also maybe give you some references if you want. So this Lagrangian here that I wrote at the beginning, okay? So there are indeed some real quantum mechanical systems in which you can realize this potential here, and so realize this conformal quantum. I know where you want to go. I know where you want to go. To say if you can use this some quantum mechanical system to actually observe the temperature. Yeah, no. This is a very good question, and it's a very important possible development.
Okay, so great. So let's thank Michele again.
Thank you.
And our next speaker is Giovanni Landi, who will tell us about Hopf algebroids and non-commutative gauge transformations.
And okay, you give me a warning. Okay. Okay, thank you. Thanks to George, Fedele, and Paolo, and the others for the invitation. And right, so I'll try to take it easy, okay? So this is based on a few recent papers that with Xiao, Han, Yang Liu, Paolo, and Chiara. Sorry, the other way around. So we've been used to the idea of Hopf algebras in mathematical physics, let me say. What we want to do here is somehow to go from quantum mechanics to field theory, in a sense. So it's like going from Hilbert space to Hilbert module. So where you substitute the numbers by an algebra, which could be non-commutative. So a commutative Hopf algebroid is somehow the dual of a groupoid. So Hopf algebra versus groups. And so now we want to go infinite dimensional in a sense. So it's a kind of a Hopf algebra of a non-commutative based algebra. Many of the structures survives, and there are many things that actually can be used as in the context of gauge transformations and gauge theories. But there are things which do not survive. For instance, one of the problems, also the source of interesting things, is that in general there is no antipode. In this in general context, it's difficult to find antipode. Okay, so try to work out a gauge algebroid of a non-commutative principal bundle, and try to use it to get a suitable class of maybe infinite or maybe infinitesimal gauge transformations. So twist the derivation, let's say, or things like that. Well, these B algebroids are actually B algebroids before is without the antipode, so they are really everywhere. So in mathematics, these are here in transverse geometry, for instance, and things like that. But let me skip this. What is the classical gauge groupoid? So this is something that we've been using since many years, maybe in a different context, but you have a principal bundle. So G acts on P, and then M is the quotient. You have the diagonal action, and now you take the orbit of the diagonal action. It's like taking one point in a fiber and another point in a fiber. So there is this arrow. Then you can move rigidly along the fiber, the 2 points. So this is the equivalence. And so you have a source and a target projection. So we are projecting from this space here to the base. There is a partial multiplication. You can multiply a point here, and another 2. You can multiply only when the second and the first of the second couplet, they are on the same fiber. So there is a partial multiplication, and there is always the inverse. You just go in the other way. So you reverse the arrow. And what is a bisection? A bisection is really a way to give a gauge transformation in this context. So it's a map from M to omega, which is right inverse to the source map. So you take a point here, and then you just go up here, but then you also want go somewhere else there. And so it's a right inverse to the source, and you are moving also the point on the base, so getting a diffeomorphism. It turns out that if you take all these bisections, they form a group. There is a well-defined multiplication here, and there is an identity, and there is also the inverse. The inverse is rather complicated because you have to invert the diffeo, and then you have to invert in the group point. The vertical bisections also form a subgroup. Now, it's a classical result that the group of bisections is the same as bundle automorphisms, and the vertical one, these are gauge transformations. So they are the same as the gauge transformations. So you can use them to study gauge theories. Okay, so I wanted to somehow associate a similar object to a non-commutative principal bundle, which again is not so unknown among this audience. So you have an Hopf algebra. This will be your structure group. You have an algebra A which carries a coaction of this Hopf algebra. I will write it in this strange manner here. There is a leg in A and a leg in H. You take the coinvariance for this coaction, and then there is some technical requirement. So you want that some principality. So there is a canonical map, which is called canonical Galois map, which goes from A tensor A over B. This is the fiber product. And then you go into A tensor H, and you want that this is an isomorphism. Okay, so if this is an isomorphism, then you say that this is an Hopf-Galois or extension of a principal non-commutative bundle. There is also another map which plays a lot of a central role. I mean, it's just essentially is the inverse here. But okay, so there is some, again, some strange notation which turns out to be actually quite useful. Once you have just played a little bit, this is quite useful. Actually, okay, there is also some technical condition, but since I don't have much time, so I will skip. So there is a technical condition that you on the class of this bundle, and so in which sense we are dualizing a principal bundle. So if you have a group, if you have then an action on the group or on some space, and then for H is the dual of the group. So these are functions on the group. Then you have the coordinate algebra on P and the coordinate algebra on P over G, so the quotient. And so you are just working out what I called it before an Hopf-Galois extension, because the bijectivity of this of the canonical map is really the principality of the action. Okay. Gauge transformation in this context is not so easy. It's not so easy because there are, of course, the non-commutativity overall, and so there are consequences. So there is one way is to just take things which are really just invertible equivariant maps, no additional requirement. But this is really too big, even in the classical situation, is too big. Another thing is that you ask them to be algebra morphisms, and it turns out that this is very small. So there must be something in between, or you have to restrict your class of examples. In this, we have this paper in progress with Paolo, where maybe gauge symmetry infinitesimally, rather than being a group or whatever, is rather a braided Hopf algebra of symmetry. This seems to be working quite well, in the sense at least you get the same amount of information that you have classically. In the sense, roughly, as a vector space, you have the same thing as classical, and then you have to change the multiplication rule. You have to change the co-multiplication rule. But somehow I want to go in a slightly different way, because I want to use this idea of algebroid and Hopf algebroid, and I also want to give some explicit example for which you can complete the program and construct even an antibody. In fact, an entire class of examples. Okay, so again, I told you before so this is the gauge group, the gauge group. So the vertical automorphism, this was the commutative case. So the vertical automorphism is written here. You have some map F from A into A. A is the role, plays the role of the total space. This is the algebra of functions on the total space. It's equivariant, so you want that there is some equivariance with respect to the coaction of the structure group, or the structure of algebra, and you want them to be the identity. So this will be the group of gauge transformation, which will be exactly the analog of the vertical automorphism of the bundle. So in the non-commutative case, you just do exactly the same thing, because you have this coaction, so H coaction A. Now you take all unital algebra maps from A into itself, which are equivariant. So the way to express the equivariance with this notation is in this manner: 0, 1, 0, 1. I recall again that the 0 is somehow the leg in A, and the 1 is the leg in H. There is again also some technical condition that seems to be necessary, but maybe not. Somehow in this paper that we are working on, it seems that we are able to overcome this technical, this additional requirement. So, okay, but I will not say too much about that. Let me tell you some example. In particular, this will be U1 bundle. So this will be monopoles bundle. Algebraically, they are the same as a graded algebra. So you break your algebra, the total space algebra, you break your algebra in pieces which are labeled by the element in the group. So in particular, if you have U1, then you have that your algebra is graded here by an integer. And in fact, this integer can be given a physical interpretation. This integer here is really the monopole charge. Somehow you have on this non-commutative area, B here will be, let's say, for instance, some sphere. You have this A1 and A to the minus 1 of AN in general. These are vector bundles, in the sense that these are finitely generated and projective modules. So these are the analog of section on a vector bundle. So these are in fact monopole kind of line bundle. And out of this, the monopole and the anti-monopole, and you construct some kind of creation annihilation operator algebra. It's really in a Fock interpretation, and you can reconstruct everything up here. You make the condition for this to be an Hopf algebra if and only if the algebra is strongly graded. I mean, in general, if you multiply any two of these spectral pieces, you get in the product one. But if you get exactly the equality, then this is strongly graded, and this is exactly the condition for the map before to be an isomorphism. So it's really the same thing. And there is plenty of examples then in this context. And the point is that now, if you want a gauge transformation, then this must be equivariant. So this means that F must respect the grading. So this means that you can just give the value on A1 and A to the minus 1, and then you extend it as an algebra map, or maybe as a derivation, or maybe as a suitable twisted derivation. explicitly, just to give you a non-commutative monopole bundle. So you have this Podolak sphere, and you have this U1 bundle. So the total space is this SLQ2, the algebra again, and then you have really an explicit coaction, and then you have the sphere as the coinvariance, and then you can explicitly write everything down there. And in this particular case, from what I said before, that you need to preserve the grading. Then the most general gauge transformation is this object here, A, C, D, B, where the generators of the algebra. Now here is the problem that I was already telling you, is that in the classical case, Q equal 1, X here, you really have only one X, only one function. But this function is any non-vanishing function from S2 into C. So your gauge transformation are maps from S2 into C star. This is no longer true if Q is different from 1. So if you just want to preserve the algebra relations, then you kill almost everything. You really go down to the classical, you really go down to C star, so the classical part of your SL2. Okay, this is another technical thing. Okay, what is now, sorry, now I'm a little bit less, just the next step somehow. So what is an Hopf algebroid? What is really a B algebroid in this context? An analog of the gauge groupoid before. Like I said, it's like instead of aiming B, if you have the complex number, say, then really what we are doing is this is an Hopf algebra. So you are really working out an Hopf algebra. Now you have an algebra, so things are a little bit more complicated, and you have what is called the B ring. So this is a ring over an algebra. So you have a B bimodule with two maps. And then you can essentially, these two maps are the source and target map. I'll show you in a moment. And you have also a co-ring structure. Again, if B were numbers, this would be really a coalgebra. So you have again a bimodule, you have a coproduct, and you have a co-unit. No antibody, I told you. So the antibody is a bit really complicated to work out in general. And in general, it does not exist. So if you put together the two structures, so a left B algebroid will be a B opposite ring and a B co-ring, and there is the analog of the source map, the target map, and there are some compatibility conditions. So the bimodal structures of the ring and the co-ring must agree via this source and target. The coproduct is essentially restricted because, again, there is a partial multiplication. There will be a partial coproduct. And then you have some condition on the co-unit. In fact, you can also give the notion of an antipode, and which is slightly more general, of course, of the case of an Hopf algebra. In the case of an Hopf algebra, is essentially, I mean, you have that SH1, H2 will be really epsilon of H. But here it's more complicated. Okay, so if there exists an invertible antibode, this must satisfy some compatibility condition, which are the, of course, again, the generalization of the usual antibode. In general, such an object does not exist. In general, it's difficult. In general, it's impossible, in fact. Even if some simple, very nice example, it's impossible to work out the inverse. So the antibody, in a sense, look, it says so roughly is the inverse. And okay, so here it is, the B algebroid that I would like to propose as the analog of the gauge groupoid. So again, we have this principal non-commutative bundle. And I recall that we had this right coaction, so the leg in A and the leg in H. We had also the inverse, the translation map, which these are elements in A. So, like you do the diagonal action, you now take the diagonal coaction, and you work out the the coinvariant elements of the diagonal coaction, and you can give to this a structure of a B ring and in fact a B algebroid. So there is a co-multiplication, so there is a co-unit, there is a suitable product, and there is a target and source maps. No antipode. But all this is really the analog of the gauge groupoid, the dual version of the gauge groupoid. And you can construct the notion of bisection. It's slightly more complicated, but it's not like before. But it's essentially it's very similar to. I mean, there is some technical requirement here, bilinearity, associativity, and so on. You can take the set of all these bisections defined as map from the B algebroid to B, so they have to invert the arrow. So classical will be from M into the what I was calling omega, so the diagonal action of the group. You can make it a group. We can use the convolution product to make a group out of this object. So in this, and you use all possible structures. So here there is the usual convention that the co-product is a leg in the first component and a leg in the second component. It's very useful to use this notation, but okay. So this is the analog of, and there is a group isomorphism, exactly like it happens classically. There is a group automorphism between gauge transformations as automorphism of the algebra, which are equivariant, which are vertical, and these bisections. And you can write explicitly from a bisection, you go to a gauge transformation. For a gauge transformation, go to a bisection. In fact, this notion of bisection goes much more general. Of course, you need to give all sorts of conditions. So for the principal non-commutative bundle, all these conditions are essentially easy to work out and to at least to see what they are. In general, it's more complicated. Here is the example that I was giving before. 5 minutes. Oh, ship. Oh, here is wow. Ship was French. And so, okay. So here is the example. Okay, and we can work out explicitly the example, and in particular now there is the antipode. You can construct an antipode, and the antipode is essentially the flip. So you see you have two copies here. So you have, these are the generators. A, B, C, and D were the generators of SL2. So you just take these are the generators of your group of your algebroid, and you have all the structure are there. And there is in fact this also the antipode, which is simply the flip. And so at the level of your algebra, this is what done. You can work out all the conditions. All the conditions are satisfied. And again, you recover the gauge transformation using bisection. Again, you have this problem of S2 into any map when you have, we are classical, or you go to C star when Q is different from 1. There are all sorts of additional examples, really. This really may work out pretty well. I mean, apart from these technical things, okay? There are these SU2 bundle over the theta spheres. There are all these orthogonal bundles over the even, sorry, this is supposed to be 2n. There are also examples from Q geometry, okay. In this context, one may think of change. Instead of taking automorphism, one may take derivations, so infinitesimal gauge transformation. And so Lie algebras of a suitable bisection. Again, this works. And maybe this is coming with Paolo and after with Paolo and Chiara. So maybe there are braided version of them, but I mean, this is back far away from. Let me just also mention a class of very interesting objects which are non-commutative principal bundle over a point. I mean, classically, this will not exist. Everything will be trivial. But now, now there are interesting example of non-commutative principal bundle over a point, over a single point. This is a purely non-commutative effect. For instance, if you have a group of algebra, then equivalence classes of Galois objects. So this will be object for which the base algebra will be just a point. So the algebra of a point. So this will be C. And so here is this. These are infinite dimensional objects. So there are infinitely many isomorphism classes of Galois object of CZR. Another beautiful example is this Taft algebra, which is some kind of a truncated fuzzy torus. So you have a generator here is Gn equal 1, then you have Xdn equal 0. If Xn is equal to 1, this is again the non-commutative torus. But on the non-commutative torus, there is no Hopf algebra structure. If you put the 0 here, you do have an Hopf algebra. This is a beautiful example of an algebra which Hopf algebra which is neither commutative nor co-commutative. And the equivalence classes of non-commutative principal bundle over a point, which have this Taft algebra as a structure group, it's really labeled by a complex number. So there are many of these things. Yeah. And if n is equal to 2, this is the Schwiedler algebra, which was also mentioned before. And what you find out is that in this context, in fact, now your B algebroid is automatically an Hopf algebra. There is an antipode. And now you work out the bisection. This will be just characters. So the gauge group will capture the character of this algebra. Again, it's a little bit too commutative. So, okay, there are interesting cross-module structure and so on. We are only at the beginning, and I'm at the end of my talk. So thank you so much.
Thank you very much. Questions?
Let me start with the first question. Or maybe I will have two. I'll have two. First question is, I mean, the typical example of U1 bundles, I mean, are, say, in a sense, very, very non-commutative are the higher dimensional tori over, say, non-commutative torus, like three-dimensional torus over non-commutative torus.
Any strongly graded algebra.
Yeah. So then, what would be this groupoid there? I mean,
will be just essentially the tensor product of the total space algebra with itself, modulo the diagonal network.
Okay, so
the group is easy to work out. What is the Okay,
thank you.
It's exactly the same strategy for especially for U1 bundle. It's really, in fact, in the example even on the polar sphere, I really took tensor product of generators.
Yeah.
So the tensor product of generators is essentially the one which carries, I mean, A and C, they go like Z to the -1, and B and D, they go like Z. So you just put together one of this column and one of the other column. There will be exactly a similar effect. You have two copies, but then you cannot take all then you take something of valence n and something of valence -n.
And the second question is, what about the star structure? And well, say some.
The star structure, that's a very good point. The structure is a little bit delicate. You can ask the gauge transformation to be algebra map. This works in many cases, but not in general. You need a slightly more complicated thing. It works in all these theta cases. it works also on the monopole, but it works really well for twists, but in general it's a bit delicate. That's why I wrote SL Q2, not SU-Q2. Okay. Yeah.
And the differential structure is less.
What do you mean, the differential structure?
So can you go to something like having?
Well, if you have a calculus, so let's say on quantum, and then you can bring it up.
Okay. Yeah. Thank you.
And you can even give gauge. We can even gauge connection in this context as breaking a suitable sequence. Yes.
Are there any? I don't see any questions online, so we perhaps have time for a short question here.
Okay, thanks. So you showed the principal bundle with U1.
The principal bundle?
With U1 structure group, right? But let's take a quantum SU2, for instance, structure group.
It works.
So but you get, my question is, you get a group of gauge transformations. Wouldn't you expect a quantum group?
If I do like I did, we would, in fact, braided Hopf algebras. I mean, a quantum group will be complicated. This is an infinite-dimensional object, the gauge transformation. So you could take formally the algebra of functions on it, but it's a mess. It's a total mess because this is an infinite-dimensional object. You can go with the infinitesimal gauge transformation. So this is a Lie algebra. Then you can work out the universal enveloping algebra of this Lie algebra. It is more manageable, these things, and you probably will get a braided, in some sense, Hopf algebra. Again, in this paper which I'm working out with Paolo and Chiara, there is a class of coming from the twist, all this theta you can braid. You can use the Drinfeld twist or the square or the square of the Drinfeld twist to braid everything. In general, for quantum SU2, again, will be, I guess that again will work, but there the structure is not triangular any longer. It's non-triangular. It's so much more complicated to work it out. But I will probably the object that you will get at the end is a braided for the infinitesimal part. Then for the group part will be for the infinitesimal part probably you get a braided Hopf algebra of braided derivations. Let's say.
Okay, thanks.
Wonderful. So let's thank the speaker once more. And we follow with another local speaker. Who is Rita Fioresi, who will talk about quantum principal bundle.
Sorry, I think you need this, no?
So can you hear me? Okay.
Looks good. We need to wait for your slides though. Okay. So our next speaker is Rita Fioresi, who will talk about quantum principal bundles and non-commutative differential calculus. Go ahead.
So this is so how do I point? Here is how. Okay, first of all, let me thank the organizers for the wonderful really conference they're having here, and it's an honor to be here. I'm very happy. So I'm really glad that Gianni introduced for me the quantum setting, so it'll be much easier. So I have a first slide with a bit of plan and motivation. So first of all, yeah, I will speak about how I became interested in these problems. Then I will say something about the philosophy of quantum principal bundles through sheaves. And in particular, I'm interested in this principal bundle. I will also try to motivate why this bundle is more interesting than the general setting. And in the end, I will speak a bit about the differential calculus. Here, I put a bibliography that, of course, is by no means exhaustive, but is just what I use in this talk. And of course, there are many people working on the same topic, and to say the least, for sure, Paolo Aschieri, that is my collaborator, but Giovanni Landi just spoke, and Chiara Pagani, and many others, in particular the people from Prague, which are really looking at the same problems, which are Wakala, Strang, Carotenuto, among others, and Krutov, and so on. So, I mean, there is really a vast community working on this, and I did not, Brzezinski, I mean, many others, Majid, Bags, and so on. So I didn't try to make an exhaustive bibliography. So first of all, let me give a motivation why I became interested. I was interested about quantum groups as a possibility of giving quantum symmetry for the Minkowski space. And I write the word super in parentheses because everything I'm saying really has almost straightforward the generalization to the super setting. So when you look at the Minkowski space, you want to realize its quantization together with symmetry. So you realize this as an homogeneous space. So that's the reason that got me into this. Moreover, there is the very interesting possibility of doing quantum Cartan geometry, Cartan connection, and look at bicovariant objects that are so interesting for physics. And yeah, of course, I forgot to mention Latini, which is another of my collaborators that is looking into this. And then, yes, we would like to do a non-commutative supergravity. Yes, non-commutative super differential forms. Castellani spoke about something yesterday. This is, again, a very interesting topic. I mean, this is all in the background. And today, I'm going to give you a little glimpse of what, I mean, the steps you are taking towards this very ambitious program. Okay, so this is... so let's start. Why do we need to look at quantum principal bundles using the Schiff theoretic language? It seems to be crazy, right? Why would you do that? And let me try to look at the definition of what is just a P principal bundle. So I'm really sorry about this notation. I know P is used to be the total space, but I want P to be a parabolic subgroup. And so for this reason, I call it P. So you have total space E. And you want a projection on to M, which is the quotient of E mod P. And then you want an action on the right on the total space and a transitive action on the fiber. And then you want the condition of local triviality. I mean, I'm sure everyone knows this, but I'm recapping these points because they'll be very useful in the quantization. So our phi model is this one, and again, in our paper, we work out more general cases. I will say a few words, but just to understand. So look at the parabolic here. And so when you look at the quotient of SL2 by this parabolic, which is actually Borelli, is a very simple situation, you get P1C, the complex line, and this is non-affine. What does it mean? That if you try to construct a global holomorphic functions on this P1C, you find just the constants. Why is this important? Because if you try to do the quantum group approach that Gianni described very well just a moment ago, you need a global algebra to do your game here, but you don't have this algebra, right? So that's the point. So when you look at the projective objects, they're covered by affine, but they don't have a global functions that are intrinsically associated with them. So let me go to the quantum world. So what do we define as the quantum ring space? So you want to take already from the beginning a Schiff theoretic approach, and then you take a Schiff over a topological space. So let's look at a classical case. Again, this is a simplified situation. So you're looking at P1C, and this is totally classical for the moment. We'll go to the quantum very soon. So you want to cover by two lines, U and V. So these will be complex. So there is a complex numbers, this is again the complex numbers. And you want to look at the algebraic functions. So I look at polynomials here, but you could do the holomorphic, absolutely, it is the same thing. And then you want the compatibility, which is the change of chart. This data that I'm writing here, so telling you what are the functions on one open set, what are the functions on the other open set, and then how to pass from one to the other will tell you a sheaf on M. Okay, this is a crash course on sheaves. Of course, there is much more than this. And then we want to do this in the quantum setting. So we want to give, so we start from a quantum ring space. So we start with a space that could be, for example, a flag, or a flag quantum manifold, or we could start with whatever, I mean, really like a projective quantum space. And then you take an Hopf algebra, and you have to think of it as the function algebra of a group P, maybe a quantization of it. And then you define a quantum principal bundle using a sheaf language. So let me show. So you want a sheaf of H commodule algebras, and then you want a covering on your base space so that the co-invariants with respect to H coincide with the functions on the open. So if you remember what Gianni put on the slide, Gianni put exactly this condition globally on the algebra of functions on your object. Here we do it locally because we don't have in general a global function algebra. And then you want the locally cleft condition. I'm being very quick on this point, a technical point, because so the H commodule structure encodes the right action of the group on E. And the locally cleft condition encodes the local triviality. And of course, this is much more refined than this, and we're writing together with Thomas Weber. We don't have a publication yet, but we soon will have where we explore much more this condition. Okay, so it's very fast and necessary. So let's see with this point of view how you write a classical principal bundle. Okay, so you look at the parabolic inside SL2C, okay, and then you define a sheaf, which is the ring of polynomial functions, not on the whole group, where you take A to be invertible, okay? So this element here is invertible. And then you get another open where you take C to be invertible. And then, of course, you have to tell me the sheaf on the intersection. And that is where you invert both. And then you have to tell me the restriction maps and so on. Of course, I don't have the time, but you realize what is the game. You get an open cover and you define the sheaf. And then you discover that it behaves very nicely. So it will have a coaction of the parabolic. So the parabolic is obtained, as I said, by looking at these triangular matrices. I'm writing in this way, which is very suggestive, because of course this matrix has no sense. These are the generators, but that's the typical quantum group notation. And you have that this natural right coaction will extend to F. Now it is very surprising that this very simple and naive construction will generalize to the quantum setting, not just for SL2, but for the quantum SL2 for a quantum algebraic group. So all possible algebraic group. And this is becoming more technical, but I will give you this example. So now we are leaving the general setting of the definition where I take a generic E over E mod P and I look at just the group. So I look at a group and I look at this particular principal bundle. Let me first, before I give you the theorem, give you what I said just a moment ago. So we're looking at SL2Q, which is given by the Manning relations that either you know them or you don't. And if you know them, fine. If you don't, it's just a quantization of this object, of the algebraic functions. And then you repeat exactly what I did before. And it works. It works great. So you can define a sheaf on this. Now you forget. So you have this thing here, UV and U intersect V, which are true open sets, but you forget about them and just look at these rings. Okay? And this data will define a sheaf, and this sheaf will have a coaction, and everything will be fine. Sorry, I was very fast. And everything will go fine. We'll go also to this F, the coaction. And the co-invariants will be for each open set exactly the functions on the base. So it works as you expect. Now, as I said, we have a general theory. You take a complex semi-simple algebraic group. You take a parabolic subgroup. You take a quantization as you like. There are many such, fine. And then you take a quantum section. This is a very nice object that I described with Ciccoli and Gavarini, my co-authors. And this controls a ring of algebraic functions on the quotient that correspond to a projective embedding. So this quantum section is linked to a quantum line bundle. This theory was developed in the work with Gavarini and Ciccoli. But what is more interesting for us, in that work, we did not realize that this is a work with Aschieri and Latini, that actually this quantum section gives us way more. It will give us the open cover. Because if you look at delta, the co-multiplication, this second di will give us the open cover of G, which behaves very nicely. And this allowed us to define a quantum ringed space. So look at this D. This is one of these just one element in the algebra of functions of the quantum groups, this of algebra, that gives you everything. So this defines a quantum ring space, and then using this, so this SI means that I'm inverting this DI. This defines a sheaf of all Q-module algebras. The covariants are what you totally expect, the algebra on the space, so locally behave nicely. And if it is locally trivial, if it is locally cleft, we have a quantum principal bundle. So this is the main result that we have in that paper. I'm, of course, simplifying. Let me go to the next situation. So let me go. So this is actually, what can I say? I'm hiding. How much time do I have? 10 minutes? Okay, great. So I'm hiding a lot of difficulties here because I just wanted to say that this D is really coming out from algebraic geometry, is a quantization of a line bundle. So line bundles in the classical algebraic geometry will give us, through a character of this ring, an associated bundle to this that will give us the projective embedding. Not all line bundles will work. So we will have to choose a correct one, called ample or very ample. We need a very ample one. We need the algebra functions to be generated in degree 1. So I'm just telling you that there are difficulties in this construction, but these difficulties are happening at the classical level, because once we go to the quantum, everything will go really nicely. The real hard quantum part comes with the OR extension, because if we want to localize and get to local situation, we need to look at an OR element, and we have to assume that this is OR. Now, the problem is that when you look at concrete quantum algebras, OR elements are not very many, but in the example of the quantum money relation, if you look at this D as a quantum minor inside this algebra, indeed it has this condition. And this whole condition was proven by Skoda. And so we borrowed the result by Skoda, and we are able to construct this bundle. So it's very important. Now I go to the next level. So I've constructed this quantum principal bundle, and I want to see if I can build a differential calculus. Again, this is work by Voronovich, Hermison. There is a lot of people that started this work, and of course the Prague people have dwelled into this. They've produced many examples and theories, and we are doing our little piece of work here. So we let's look at the local situation. Suppose we have an Hopf algebra. Suppose we have a right H comodule, so structure. What is this differential calculus? We want to define a first order differential calculus of algebra as an A by module omega with a C-linear map, the differential, which satisfies some obvious property, the Leibniz rule, and we want the H covariance, we want a coaction. Again, this is notation that Gianni introduced, so this F0 and F1 refer to this coaction and co-multiplication, okay? So this is very natural, and this was again done by Voronovich, who constructed a bicovariant differential calculus on Hopf algebras that is quantum groups. Here we are interested in right H comodules, and for this reason we had to modify all this, and this is joined with Aschieri, Weber, and Latini. Now, how do we translate this picture into the sheaf framework? So first of all, we take a quantum space. What does it mean? Again, we have an open cover and we have a sheaf OM on this open cover. Then we want a quantum principal bundle that is a sheaf of H commodule algebras, which locally, you see, behaves nicely. So what does it mean? That the co-invariant for the H action is the algebra on the base. So M is the base of my principal bundle. And we have that the locally cleft condition. Again, I'm hiding a lot of technicalities because this is not, I mean, if many of you here know what I'm talking about, so you know that it's not as easy as it seems. Now, what is an H covariant first order differential calculus on this quantum principal bundle F? We take a sheaf of H covariant algebras with an H comodule natural transformation. So the differential D is not anymore as before, you know, this map from an algebra to omega, which is a bimodule, but becomes a natural transformation. Why? Because we have sheaves, and sheaves in some sense are functors. So you want this object. And locally, what does it mean? If we cover our space with an open cover, we want the Leibniz rule and this condition. The bimodule can be written in this way. And again, we have the H covariance. This condition is local, again, is the only possibility. Now we can go further and define what are the covariant forms. And we have this result, which is work in progress. The H bicovariant finite order differential calculus on the Hopf algebra of the quantum group, this quantum group, which is produced by Voronovich. So we borrow Voronovich result, induce naturally an H covariant differential calculus as quantum principal bundle. So this was a bicovariant on this Hopf algebra, but no, we're doing more. We are showing that it satisfies this definition that we gave before, and so we view OQG as quantum principal bundle on this. So there is a sheaf obtained by this group and viewed as a quantum principal bundle on the base, and then the Voronovich calculus will induce naturally, or any other calculus, naturally the calculus on the base. And then again, the finite order, first order differential calculus on this Hopf algebra will induce this on the base, and the differential forms on the base are exactly what you expect. We started working also on quantum vector fields, on characterization of the so-called horizontal forms, but we don't have a definite, I mean, I don't want to give, this is really work in progress. Now I want to give you my conclusions, the bottom line. So we give a notion of quantum principal bundle of a non-affine base. So I'm writing here the real forms of what I described. So SU22 is a real form of SL4C, which is the conformal group. And this is the conformal space. And then the Minkowski space appears an open cell inside this Grassmannian. So we're looking at the complex picture, but evidently the real picture is very, very interesting. And of course, as they asked Gianni, what is the C star? Yes, of course, there is C star structure that must be explored, and we have not done it yet. We have defined a finite order calculus in this setting. And as I said, we want, so there is a plan to go towards a more physical application. We have defined this first order differential calculus. We want to go beyond. We want to discuss vector fields. We want to discuss connection. We want to go towards this type of study. And this is it. And thank you for your attention.
Thank you very much. Plenty of time for questions.
Okay, thanks. So if I understood you correctly, you make a quantum principal bundle over essentially a commutative base. At least you do it locally with the sheaf. At the same time, you wrote OQ of G over P. Is that, can you actually patch it together?
No, thank you. It's like so the covering is correctly you say is really an honest cover of a topological space, no quantum. But the algebras that you associate with these are quantum. So in the case of this, let me show this. Okay, so when I write OQG mod P, this is a quantum algebra over the base. So the base maybe is P1C topologically, but well, P1 is a stupid, say PNC, right? We construct the Pn, this algebra OQG mod P will be quantum projective. Okay, so we get all the results by Landi, for example, in the quantum projective space. Strange, right? Topologically is classical, but the algebras are quantum, right?
But is there a way to kind of to localize this OQ to have or actually to reconstruct OQ in this case from the local structure to patch these?
I see you are totally on top of things. This is exactly what happens. This is exactly that. So we have the global object that is obtained by patching the local ones. Yes, it is done like this. Very geometric. Yes.
Thanks. Well, thank you. There's one more question.
Thank you very much. Maybe this will be something like adding to the previous point. I mean, in case of non-commutative algebras, there's also a notion of something like covering of this non-commutative algebras that's been developed by Callow and Mathis. And I mean, you can associate with it, and actually this somehow relates to the previous talk as sort of canonical coring. So there's a notion of canonical coring associated to the non-commutative covering of non-commutative spaces. So, and then this, I think, I mean, might be used, you know, for sort of a localization of the quantum.
So you're talking about like IATs and collaborators. Yeah, no, of course, I forgot to mention IATs, obviously. Yes, it's...
it might be used for that. I mean, this sort of...
No, the idea is, yeah, the idea is exactly that. I apologize for not mentioning. Of course, this is the same idea, but what they do it for affine. They never look at the projective flag. That is the difference, but yes, the idea is absolutely the same. Yes, indeed. Yes. I should have mentioned, yes.
Thank you.
Are there any questions online? I don't think so. Are there any more questions here? If not, let's thank the speaker again. And we have a remote speaker, Satoshi Watamura. Can you hear us? Satoshi, can you hear us?
Yes. Can you hear me?
I can see the microphone icon going up and down, but we cannot hear you. Let's try again. Can you hear us, Satoshi?
Yes. Can you? I'm speaking, talking, and.
Okay, you can turn on your video, you can share your screen, and you can go ahead with your talk.
Yes. Now, is it?
Yeah,
okay.
We can see your slides.
And hear me?
Yes, we can hear you, and we can see your slides.
Ah, okay.
So
let me start.
You have 25 minutes. I will give you a 5-minute warning.
Okay. So, first of all,
so our next speaker is Satoshi Watamura, who will tell us about metric algebroid in DFT.
So first of all, I want to thank organizers for giving me the chance to talk in this meeting. Today, I want to talk about the metric algebroid in DFT. And this talk is based on the collaboration with Karo Watamura, Miura, and Yano, and published in the JHEP. Now, so DFT, double field theory, is proposed as a T-duality invariant formulation of the effective field theory of string. The gauge symmetry is generated by the so-called generalized Lie derivative, where the diffeomorphism and the B-field gauge transformations are unified. But the main drawback of these formulations is that it is always accompanied by the section conditions or strong constraint. So gauge symmetry is closed up to strong constraint, and equation motion is equivalent to supergravity up to strong constraint, and it is consistent up to strong constraint. So it's very unsatisfying. Now, in this talk, the first part of this talk, my question is how far one can formulate without strong constraint. So our approach is using as a algebraic structure the metric algebroid, and this metric algebroid is behind the Courant algebroid, or it includes the Courant algebroid. Therefore, behind the generalized geometry or Courant algebroid and supergravity, and also keep local ODD covariance. So it means manifest local Lorentz transformation, and it is often this covariance is kept under the strong constraint, but we don't use the strong constraint. And also including the case with a non-trivial metric on the base manifold. So we don't require the flat base manifold like standard DFT. And here the ODD covariance goes as far as like a Bianchi identity and so on. But for the action, we reduce it, of course, to the OD cross OD. Now, the second part of this talk is about the formulation of DFT. So far we have using the supermanifold method or QP manifold method. So there we consider the graded symplectic manifold here. So shifted cotangent bundle of the tangent bundle of base manifold. Considering pre-QP manifold and the DFT is formulated as a case where the holomorphic or Hamiltonian function theta satisfies the weaker condition. The relation is the following. So QP manifold is a manifold where the classical master equation for the Hamiltonian function is hold, and it is equivalent to the Courant algebroid. And then pre-QP manifold, we don't require this classical master equation. Then this corresponds to the actually metric algebroid, which we are going to talk. And then for the DFT, we require a weak closure, which corresponding to the weak master equation. And this includes the section condition and leads to the DFT. But the drawback of this QP manifold method is that there is no dilatons. And we use the so-called Dirac generating operator, which is used by the Alexeyev Shu for Courant algebroid. And we use it for the DFT or metric algebroid. And this DGO is just a Dirac operator, but it contains all information, so all fluxes in DFT. And the outcome here is that the Lichnowitz, generalized Lichnowitz form of the DFT action, which is a generalization of the formula given by Coimbra-Minassian for supergravity. So the metric algebroid is proposed by Weissman as an algebraic structure of DFT, and we follow this proposal. So Courant algebroid, first of all, is now in the meantime, it's known probably the people. So it consists of the vector bundle and bracket and this anchor and fiber metric and the differential. And there are several relations among these operations, but actually, simply we need three relations, which we call axioms. And these three relations is sufficient to derive all other relations. Now, metric algebroid is the same setting like a Courant algebroid, just we drop this Jacobi Leibniz-like form of the Jacobi identity. So we have only two relations in the metric algebroid, and it's this A and B, and the deviation from the Courant algebroid is characterized by the following maps. So we call L and then L prime. So L is just the Jacobi identity, which is dropped, and other form like measuring the difference between the structure functions of the algebroid and structure function of Lie bracket. Here, this is a Lie bracket on the tangent space. Now the relation is the following. If the L and L equals 0, then actually L prime is 0, and then it reduces to the Courant algebroid. And if L is 0, but we can still require, L is not 0, but still require L prime equals 0, then it's called pre-Courant algebroid. And the metric algebroid is the most general case where the both are dropped. So an algebroid, it's a biggest algebroid, but a DFT for DFT is too big, so DFT is in between somewhere here. And Segura is known as a Courant algebroid, has a Courant algebroid structure. So we are now discussing how to strict the metric algebroid to fit with DFT. So first of all, we geometrically restrict the DFT, and which is called algebroid, which is called DFT condition. So we have the metric algebroid, and we introduce the local basis where the inner product is defined like this. Then, first of all, the very specific vector bundle, which is the dimensions are the same like a tangent bundle. And then the anchor is inverted. So we can write in this way. Then we have here the so-called generalized field binding. And there exists an inner product, Tm, such that, so we can identify the inner product of the algebroid with the product in the Tm. So, and for the local basis, this product is equivalent to this product. And now we require is an ODD metric, so constant metric. Note, metric on the base manifold, which is given in this way, is not required to be constant. So we go in general manifold, on the general manifold. Now, we also require the local ODD covariance by using the tensorial property. So what is the tensorial property? This we consider for any map, phi and the argument is from this vector bundle, then consider take the function of a base manifold, and then scalar product on the argument is just like this, so it comes out from the function. And this relation holds for all arguments, then we call it tensor. And the meaning is the following. For example, we consider the flux, which is appears basic object in a DFT, and this is not a tensor. So this can be seen in the following way. So define the deviation from a tensor as the following way. So you multiply the functions on each argument and subtract the tensorial factor. Then we see, since this is not a tensor, we see some kind of formula. And usual structure functions, which is given by substituting the basis into this argument, has inhomogeneous term by this. So we take the local ODD transformation by lambda for this basis. Then we get this structure function is a tensorial transformation by lambda and gauge transformation like part. So inhomogeneous term. So checking this tensorial property, we can see that all the dependence of the local Lorentz transformation. Now, with this, we want to impose to characterize the metric algebroid, which describes the DFT, we want to impose the frame independent condition. So for this, we consider a map first, these two maps, but they are not tensors. So we cannot simply set the equal 0 to restrict the metric algebroid. However, we can construct a tensor from the above maps. And this is these combinations. So then using this tensor, we can impose further condition on MA to describe DFT. And this we call pre-Bianchi identity. And since this is a condition on the tensor, this is base independent. So it doesn't break the ODD covariance. Now we see by using the local basis EA, this maps gives you this structure functions like this. Then the structure this condition by phi tilde can be seen like this. So, and thus the pre-Bianchi identity phi tilde equals 0 gives a condition on the structure functions. And this is actually already similar to the Bianchi identity of the standard DFT, but this is covariant. But if you want to compare really the standard DFT identities, we choose that the base manifold is flat, and the metric eta mn on M is ODD, and take the flux defined by the D bracket. It means this F is defined by the standard D bracket. Then this pre-Bianchi identity reduces to, for example, in this way, where this omega ABC is Weizenburg connection, and this formula is on the local frame. And if you take the other frame, then you get a different type of the relations. And but you can get such a relation also from this pre-Bianchi identities. And this form in the standard DFT is called generalized Bianchi identity. So this reduces to the general Bianchi identity after fixing the frame. But this side is the formula, a frame-dependent formula. So in metric algebroid, we have another identity corresponding to standard Jacobi identity of Lie bracket. This means you take the anchor of these vectors, then you get tangent vectors, and then take the Jacobiator of this. Then, of course, this should be 0, but using the metric algebroid relations, we get following relations. And this is this gives you some relation for the structure functions and is related with the Bianchi identity, including Diraton. To see this, we introduce flux like this, and which UA is some ambiguity which satisfies this. And this ambiguity the meaning of this ambiguity is a little obscure in this moment, but later we discuss it. Then this this gives this type of identity, and this is again the pre-Bianchi identity of flux FA. So this and this related with the Bianchi identity of the flux, including the Diraton. We examined the tensorial properties of the other object, like eTosion and generalized Riemann tensors. And actually, eTosion is already, the standard eTosion is already a tensor, so we don't have any improvement. But the generalized Riemann tensor is has an improvement. And this is standard DFT Riemann curvature, but this term makes it covariant. And I don't discuss too detail about these formulations, but now I want to move to the next subject. So the Dirac generating operator and derived bracket formulation. So in the formulation, by using graded symplectic manifold, which we did for some years, this bracket and anchor in Courant algebroid are defined by the derived bracket. The same things can be done by using the Dirac operator, which is pointed out by Alexeyev and Chu. And for this, we introduce a so-called Clifford Bundle, which is, but the detailed definition can be found in our paper, but simply you replace the vector by the contracted gamma. So this gamma is gamma matrix, and then base are replaced with gamma matrix. Then in general, we consider this antisymmetric product of the gamma matrix and the coefficients. And then we define the degree is by a number of this index. So this is very familiar to the physicists, and define a graded bracket in the usual way by Clifford product. So you just make a product of the gamma matrices, and then this bracket is defined by this or commutator or anti-commutator according to the degree. Thus, then for two vectors, we have the fundamental relations. And in this way, the bracket defines, here not the Poisson bracket, but just standard, this graded bracket defines the inner product of the fibers. We also consider the induced connection on the Clifford bundle for given E connections in this way, then and the Leibniz rule with respect to the Clifford product. So we have connection of Clifford bundle. Then we introduce the spinner and as a module of a Clifford bundle, then Dirac operator is formally defined in this way. So using this, we introduce the three operations. Here, the simply commutation with a function and derived bracket, and also the kind of derived bracket with a vector and a function. Then we get these three operations, and this satisfies the metric algebroid axioms. So, and other maps are given by also using the Dirac operators. So then using the DGO and derived bracket formulation, we can prove formulas in metric algebroid and all pre-Bianchi identities, and so simply by the usual differential calculus and commutators of gamma matrices. So it becomes simple. And I don't go in detail here. Here we want to discuss the formulation of the Bianchi identities and also the DFT action generalizing so-called Lichner-Witz formula. So what is the Lichner-Witz formula? The original form of the Lichner-Witz formula is given by Lichner-Witz in 1963 in the following form. So square of the Dirac and minus the Laplacian gives you the scalar curvature. And it is extended, including the H flux by Bismuth and supergravity by Coimbra-Minassian. And we follow this direction. So, and first, how to see the Bianchi identity from the generalized Lichner-Witz formula. So we consider the torsion-free connections of differential generating operator. It means this covariant derivative on the spinner, and then just taking the trace with gamma number A, then you get a Dirac operator. And the relation between these spin connections and this F, which becomes a flux, is the same and is the following. Now, generalized Lichner-Witz formula is given by covariant combination of these two, so square of the Dirac operator and Laplacian. Then we get this complicated formulas. But for example, here is not the scalar, and here they are not scalar, and only the scalar part is here. So we require that all other part cancel, and then is vanish, and this gives you the generalized Lichner-Witz formula. So here the Laplacian is defined by this formula, and the important thing is there is an ambiguity UA, and this gives you the possibility to introduce the dilaton. So
you have 1 minute left.
1 minute.
Yes.
5 minutes. You said 5 minutes.
You probably didn't hear me. I gave you, but go ahead. You have some time left.
Okay. I will finish soon. Yeah. So then this relation gives you the three relations to make this Lichner-Witz formula, and they are already I gave in the previous discussion, and this is, for example, this pre-Bianchi identity, and this is pre-Bianchi identity for the dilaton flux, and this is a definition of the dilaton flux. So in this way, and then this we can show that this reduces to the dilaton flux, true dilaton flux in standard DFT by solving this relation. Now, we can do also the actions, but this Lichner's formula, this scalar is not the curvature which defines the DFT action, but this is the trace of the covariantized Riemann, just a trace of the covariantized Riemann curvature. Now, to get action, you split in the standard way, and then you introduce the compatible connections, which is only the non-zero components are in this way. So you have plus sector and minus sector, and then they connect only the plus to plus and the minus to minus. And using this, you can construct you can define the Dirac operator and then connections. Then the Lichner formula for the projected Dirac operator is like this. And we can show that this L gives you the standard DF, not standard, I mean covariant DFT scalar curvature, which is actually the action of the DFT, and the Bianchi identities, which is also necessary to define the DFT. So finally, two discussions. One, we gave the generalized Lichner formula, but and then we wanted to discuss the major part. And then because in the major part, there is also the dilaton contribution. And for this, we introduced the dilaton as a density with weight 1/2, which is proposed by Severa for Sugura. So in this formulation, we can formally introduce the dilaton in this way. But this mu0 is now the measure for d-dimensional integrations. And before integrations, we need the section conditions too. And closure of the gauge transformation should be still also discussed. So it's still before 5. Thank you very much.
Wonderful. Thank you very much. And we do have some time for questions or comments. I don't see any questions here. Are there any questions online? Okay, so we have no questions. So let's thank the speaker again.
Yeah.
This concludes the program here, but before the coffee break, we have some organizing